Okay, welcome back everyone. In this video we're going to be talking about electromagnetic waves and the electromagnetic spectrum. And so what I want to do to start out is to go back to what we talked about briefly when we were studying charges and electric fields. So this is an applet from FET. This is basically how a radio station broadcasts. Radio station has an antenna represented by this pole here, and on that antenna are some wires which have vibrating electrons. And what we know is that surrounding an electron is an electric field. And let's see if I can get that to show up. So here's my static field, and because it's an electron, the force vectors point inwards, and if I move it, you can see that the field changes. So that's not too exciting. And this is the direction of the force. So we know that the force and the field are going to be opposite each other for an electron. So the interesting thing is when we take off the static field and we look at the radiated field, in other words, if you wiggle an electron, oh, that's kind of weird, right? But those electric field lines sort of radiate outwards. So another way to look at it is kind of like this. Or if I show you the same thing with vectors, it looks kind of like this. So what this is showing is that the electric field is actually moving through space. It's propagating is what we would call. And if I were to oscillate this, well, now we have a wave. So what we're really doing is we're putting together what we studied with electric charge and electric field, and also last unit with waves. And so the point here is that there's two ways to make an electromagnetic wave. The easiest way is to just get an electron to vibrate, but you can also have a changing magnetic field. And so what we can do is take a look at a couple of pictures to visualize this a little bit better. And so this is a representation of an electromagnetic wave. So you have two things that are changing at the same time. One is the electric field, and this is represented in red. So the electric field is increasing and decreasing. Sometimes it's positive, pointing up, sometimes it's negative, and it changes both as a function of time and depending on your location. So it's kind of complex. It's a function of two variables, position and time. And you can see a wavelength like we've talked about, and this is the distance between the two maxima of the electric field. And so that's one part of an electromagnetic wave. The second part is the magnetic field, which is in blue, which is kind of wiggling back and forth like this. And the magnetic field varies as well with the same wavelength. Now, this isn't something that I can really prove to you until next year, so you're going to have to just take my word for it. But the fact that the electric field is changing really does cause the magnetic field to change. And because the magnetic field is changing, it'll cause a change in the electric field. So this is what we call self-propagating. And this is the only kind of wave that we know of. This is called, self-propagating. And I can't spell tonight. Okay? Self-propagating means that the wave continues and it travels at the speed of light, c, unless it interacts with something. Okay, so electromagnetic waves travel at the speed of light, and they travel until they come into contact with something else. And that's really the basis of what we're going to be talking about this chapter, whether it's a mirror, so reflection, or in terms of a lens, refraction. So we'll be talking about all these things. And then the last thing I want to point out in this introductory video on the electromagnetic spectrum is that there's lots of different things that qualify as electromagnetic radiation, or EM waves. Okay, and so what we have here are a variety of scales. This top one's not super useful, but you can see the radiation type, and this is going from the largest wavelengths to the smallest. Okay, so radio waves, the size of buildings, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays, which are on the order of atomic nuclei. Okay, then you have the frequency. Well, radio waves are only about 10 to the fourth, and keep in mind the equation that's linking all these together is that C is equal to frequency times wavelength. And so if you see a particular frequency, you multiply it by a wavelength, you should get on the order of 10 to the eighth, so the speed of light. Okay, so here's your frequency scale. Now notice that right here is visible light. So light that we can actually discern with the eye only takes up a small part of the spectrum. And so it goes, the spectrum itself goes all the way over a very wide range. Now this is an interesting part of the graph. It shows you the temperature that objects are at in order to emit this kind of radiation. Now objects, when they radiate, will emit a wide variety of wavelengths. And so if you think about it this way, if you think about sort of the intensity or the amount of waves that objects give off versus the wavelength, there's going to be some sort of a peak. And so what this graph is saying is that the location of this peak wavelength, or lambda max if you will, is dependent on temperature. So if I redrew this graph, let's say for fun that this was something which was 100 Kelvin. If I redrew this for something which was, I don't know, maybe 200 Kelvin, it would be a little bit different. And that's really all I'm going to go into right now, but just keep in mind that something that emits X-rays is going to be much, much hotter than something that emits infrared. And as a matter of fact, humans emit infrared radiation. So does the planet Jupiter, by the way. Jupiter also emits a lot of radio. Now, the last thing I want to point out about the electromagnetic spectrum is that there's been a lot of controversy about living near power lines. And, the question is, do power lines give you cancer? So, one thing to keep in mind is that things like ultraviolet radiation, well, that certainly is known to give you cancer. Okay? We know that if you get sunburned too many times, you could get skin cancer. And damage from that actually comes out many years later. X-rays most definitely are dangerous, and even more dangerous than that are gamma rays. So all three of these guys are called ionizing radiation because that's what they do to the ions in the atoms that make up molecules. They ionize it, and that's what causes mutations in DNA and therefore cancer. Everything below this point here, ultraviolet, so visible light, infrared, microwave, and radio, are non-ionizing radiation. In other words, they don't cause electrons to jump off atoms, and so they shouldn't, so far as we know, cause cancer. And those overhead power lines, well, they're putting out, like your cell phone, mostly microwave radiation. So and also a lot of radio. So if you have someone come up to you and say that power lines are dangerous and cause cancer, you really need to take that with a grain of salt. They are putting out non-ionizing radiation. So that's about it for this one. Next time we'll take a look at reflection and plane and spherical waves.